Serge Cantat will talk about rigidity of Hénon.
Thank you. Okay, so let me start with what I call rigidity. Let's say in algebraic or holomorphic dynamics. Okay, so what I have in mind is that you know some very low-tech feature of the dynamical properties of a map, and you want to derive from that a better knowledge, like high technology things are determined by low technology things, or even the map is determined by something. Okay, so like the slogan is like low-tech features of the dynamics of F determines high-tech. Features of F, or even maybe F up to conjugacy. When I say conjugacy, it's up to algebraic conjugacy. Okay, so that's the general type of thing you want to type of problem you want to look at. Let me try to list some specific instances of this problem. Like assume that F is conjugate to G by some smooth map, like say C1 smooth map phi. Does this imply that F is conjugate to G by some algebraic or polynomial map? Okay, so that's one instance of this rigidity type problem. Okay, so in general, such a statement is not correct. For instance, if you take multiplication by 2 on distinct elliptic curves. Okay, when I say distinct, I should write, let's say, non-isogynous elliptic curves. Okay, from the perspective of differential geometry, it's just multiplication by 2 on R2 mod Z2. Okay, so up to a real analytic change of variable, your two dynamical systems are conjugate to the same one. Okay, there is a real analytic change of variable which changes the first elliptic curve, let's say C divided by some lattice, and the second elliptic curve C divided by some lattice L prime to the same real analytic torus with the same dynamics. Okay, so this multiplication by 2 on this elliptic curve and multiplication by 2 on that elliptic curve are C1 or even real analytically conjugate, but are not holomorphically conjugate. So are not conjugate by an algebraic map. Okay, so this is a counterexample to this philosophy. But the idea should be that, in general, some smooth conjugacy implies some algebraic conjugacy. Okay? Otherwise, we should understand the counterexample. So the map should be spatial or weakly spatial. Okay. Okay, here is another instance of very low-tech knowledge that implies high-tech. So suppose F and G have a common orbit. Okay. Okay, and assume that the orbit is Zariski dense. Okay. Then you want to say that F is equal to G maybe. Okay. So the answer is yes, and it's obviously yes if an orbit is a parametrized orbit. Okay, so by this I mean that you look at the sequence Fn of x, x is your starting point, and you assume that Gn of x is equal to Fn of x for every n. Okay, then call this point xn, so this is xn, and then f of xn is what? It's xn plus 1. Okay, but it's also g of xn. So f and g, they coincide on a Zariski-Dense set. So f is equal to g, okay? So this, for instance, is obvious. Okay, but now look at the orbit as unparametrized sets. So you assume that the set of points you get in your orbit by f is equal to the set. Okay. Does this imply that f is related to g in some sense? As sets, okay. And here there is a trick, so I let it as an exercise. Suppose for simplicity that f, g are endomorphisms of P1 of some degree larger than 1, and define over Q bar. Okay. Then you know that when you take an orbit, and also I assume that x is in Q bar. Okay. So what you can do is you can look at the height of Fn of x. Okay, so what you get is a series of numbers. So to each point in this set, you get a number which tells you the arithmetic complexity of the point. Okay, and this sequence of numbers grows exponentially fast. Okay, so in fact, these points are arithmetically marked by n in some sense. So you can recover the time from just the point. The arithmetic complexity of the point tells you what the time is. So you recover the time, and so you recover the parameterized orbit, and so f is g. Okay, so I cheated a little bit. Maybe f is g square or something like that. I need to be careful, but if you use this ID, you get the answer to the problem. Okay. Okay. So another type of rigidity problem is suppose f preserves some geometric structure. Okay, so for instance, let's say I work in dimension 2, and f preserves foliation by Riemann surfaces. This is something we will look at in, I don't know, half an hour or something like that. Okay. Or in dimension 1, it could be, so let me just write this example. In dimension 1, it could be a smooth line field, you know. This is something I call a geometric structure. Or you could have, on the variety where the map is acting, you could have charts to, let's say, C to the D, where D is the dimension of the variety, and the change of charts are affine transformation, so linear plus translation. So in differential geometry, this is called an affine structure. Okay. If you have such a structure which is invariant, is F spatial? Is F related to some kind of a lattice map or endomorphism of some group or something like that? Okay, another type of rigidity problem is which is clearly related to the previous one, is suppose there are some spatial regularity properties of the dynamics of F. So for instance, that Julia said, so assume that F is an endomorphism of the projective space, and suppose that the Julia set is smooth and not the total projective space, or that the measure of maximal entropy is smooth. Does this imply that F is spatial? Okay. So here the result is known, I mean, for the second sigma at least. So this is due to Zdunik and Berthelot and Dupont, and then the answer is positive. Okay. Okay. Or you can ask if F and G have the same periodic points, or the same preperiodic points, or infinitely common preperiodic points. What can you say about F and G? Are they related? And this we saw the answer with the lectures of Myrto. Okay. Another, and this will be the last feature of what I have in mind when I'm talking about rigidity, is you look at algebraic relations, like, for instance, F commutes to G, or in fact, we would like to deal with more complicated algebraic relation, like, I don't know, F to the 17 GF is FG. Okay. What can you say? Okay. So is F related to G in some sense? So for instance, do F and G have a common power, or this type of things? Okay. So for instance, so you have the work of Reed, which is classical, of Pakovich, Dean and Sibony, etc. Okay. So I list the name, or I should. I've said something at the beginning. So this is based on a joint work with Romain Dujardin. Okay, and Romain will give another talk on the same subject next week. Okay, so it's some kind of introduction to Romain. So yeah, it's a mini course. Yes, I do the easy part. You know, I list problems, and then I say Romain will answer all the problems. Okay. And also I know I frequently forget to cite people when I explain mathematics, so I should cite at least. So I will describe things which are due to Bedford, Lubitsch, Smiley. Okay, and also, yes, because in alphabetical order there is also Kim, and I will use the work of Bedford and Kim. Okay, and so that's one group of people, I will say, and Fornais Sibony, of course, and also, if I forget to say it, the work of Brunella, which was inspired by some work of Dominique Servo. Okay. Okay, so this is the type of equations I have in mind when I'm talking about rigidity. And what I want to say is that, in fact, not all of them, but many of them are related. Okay, so for instance, a problem of rigidity under conjugation is related to the existence of invariant geometric structures, smoothness of Julia set, or measure of maximal entropy, and also algebraic relations are related to these questions. Okay. And so I would like to state and maybe prove a few statements in the case of Hénon maps, which show that the interplay between this type of questions. Okay. Okay. So I'm erasing this list of nice people, but. Okay, so first, I will explain what a Hénon map is, or more generally, what an automorphism of the plane with positive entropy is, how the dynamics is, and then I will look at some kind of rigidity statements. Okay, so I will look at automorphisms, so polynomial automorphisms of the affine plane, so over the complex numbers, so C2, with positive entropy. Okay, positive topological entropy. So it's the same as the following. So you start with a polynomial map from C2 to C2 with a polynomial inverse. So f of xy. So p and q are polynomial functions in x and y, and there is an inverse of the same type. Okay, and you assume that it has positive entropy. So this is exactly the same as saying that the degree of the formulas for the nth iterate, okay, is bounded from below. When you look at this sequence, it's bounded from below by something which is strictly larger than 1. Okay, so there is exponential growth of the degree, and then in that case the limit exists and is some integer larger than 1. Okay, so that's the same thing as saying that. And it's also the same thing as saying that f is conjugate in the group of automorphisms of C2 to a composition of Hénon maps. Okay, so Hénon maps are of the following type. So you, in coordinates, hj of, let's say, xy is what? It's aj y plus pj of x. Okay, and I can assume that so aj is different from 0. It's minus the Jacobian determinant of hj, and pj is monic and centered. Okay, so the sum of the roots of pj is equal to 0. Okay, and then this writing as a composition is almost unique. You can always conjugate by h1, for instance, to put h1 on the left. Okay, and you can do it again. And there is an action of the group of roots of unity of I don't remember which order on this normal form. Okay, but modulo this cyclic action by permutation of the hi and this action of a finite group, it's unique. Okay. No, not if I do this hypothesis. Okay, and then the Jacobian determinant of f. So the Jacobian determinant of f is the product of the minus aj, and the degree d is the product of the degrees of the pj. Okay, so for instance, you see this list of Jacobian determinants of the hj up to this cyclic permutation and this finite group action by roots of unity is uniquely determined by the conjugacy class of f. So the Jacobian of F is, of course, an invariant under conjugacy. But there is something deeper, I mean, more, I don't know, more precise. It's this decomposition as a product. It's almost invariant. It's almost a conjugacy invariant. Okay. Okay. So now, what is the dynamics? So let's look at the dynamics of. I will do it for a Hénon map like this, but then the same conclusion applies to F. So, yeah.
You said the list of the AJ and the PJ is unique, but maybe you can tell me that.
So you can, yes, I don't want to discuss this because this will not play any role in my talk, okay, but this will be important for Romain, so I just wanted to warn you that this, so let's call this decomposition the normal form of F. So the normal form is an abuse of notation because it's not unique. First thing I can do, I can permute cyclically the HI. Second thing I can do is, I can conjugate the HI by diagonal transformations, diagonal linear maps. So I can multiply X by some number alpha and Y by some number beta and look at what happens. And then for certain alpha and beta, which are roots of unity, then I act on this normal form and I get another normal form of the same type, so monic and centered. Okay. But modulo this finite group action, this is unique. Okay. And in particular, modulo some roots of unity and permutations, the AJ are attached to F. In fact, you can recover the AJ by looking at what happens at infinity. Let me describe here. Okay, so what is the dynamic? So take a large bidisk. So let's say V is xy in C2 where X and Y, both of them are in modulus at most R. Okay, are large enough with respect to the coefficients I see. Okay, and so this here will be V plus. So, and here this is V minus. So let me write V plus. It's xy such that y is big and y is larger than x. Okay, and then V minus is symmetrically defined. Then the dynamics of F is as follows. When x is big, because the degree of P is at least 2, this term is the biggest one here. So if x is big, I go there. So the dynamics is like that. And here, I don't know what happens in V. This is where the Julia set will be. Okay, so let's say K plus the set of points with bounded forward orbits. K minus, okay, is a set of points with bounded backward orbits. Okay. And this is the same as C2 minus the point that eventually end in V minus. So union of the preimages. So H is my Hénon map. Okay. J plus, will be the boundary of K plus. And the same for J minus. Okay, and so the picture is something like this. So you have like K plus is something which is like that. Okay, and J plus is the boundary. So let's see. K plus and this is J plus. Okay, and the intersection is the Julia set for forward and backward iterations, and intersection of J plus and J minus, and it's Okay, so this is just a topological picture. And from this, you easily get that the stable set of K, so points in C2 such that the orbit in forward direction will converge toward this compact set K. This is the same thing as K plus. Okay, so here it's very basic, and now comes a complex analysis and then a Pessin theory. So you can look at the function G plus, so of xy. So I write it for Hénon maps so that you can just look at this specific formula and verify that what I say is correct. But then a little bit more analysis says that the same decomposition of the dynamics and the same results are also valid for F, okay, or for the composition on the right. Okay, so it's a limit when n goes to infinity, 1 over d to the n, and you look at the logarithm of the norm of the, let's say, hn of xy. So in fact, log plus is what you need. Okay. Okay, and the point is that this is a continuous function. And you can define t plus, which is ddc of g plus. You can do the same for g minus, and then you can take the product. It's t plus wedge t minus, and this is an invariant probability measure. Okay, for H or for F more generally. Okay. And in fact, this measure is mixing, and so this is a unique measure of maximal entropy. Okay. Okay. Also, I say it now, but in fact, it depends on what I will say afterwards. Mu h also describes the equidistribution of periodic points. Okay, so periodic points of Hénon maps are isolated points. I mean, if you fix the period, so you can put Dirac masses on these periodic points when the period is fixed, and you divide by the number of points you have, and you take the limit, you get mu h or mu f. Okay, and it's the same for saddle periodic points. So periodic points such that the differential of h at the periodic point of h to the period has an eigenvalue which is less than 1 and an eigenvalue which is larger than 1 in absolute values. Okay. And so what is the relationship between t plus and j plus is that j plus is the support of t plus. Okay. And this is much better than that. In fact, by a result of Fornaes and Sibony, so all what I was describing here is due to Bedford-Lubitsch-Smiley, and here it's a rigidity result of Fornaes and Sibony, is that T plus is, so up to multiplication by some positive real number, the unique a closed positive current which is supported on J plus. Okay. Okay, and so then the last thing that I need is the relationship with stable and unstable varieties of saddle periodic points. So assume P with some coordinates is saddle periodic, or here I will directly assume fixed. It's a saddle fixed point of F. Okay. Then, so because it is a saddle point, you have the stable manifold of P. You have the unstable manifold of P. So the stable manifold associated to P is just a set of points in the plane with forward orbit converging to P. Okay. And both of them are Riemann surfaces, and they are B-holomorphically equivalent to C. So there exists, let's say, some psi SP that goes from C to C2, okay, which is a holomorphic map. And psi PS is one-to-one onto its image. So and the image is a stable manifold. So it's a parametrization, an injective parametrization of WUP, and I will assume that it maps 0 to P. Because this is the meaning of being holomorphically equivalent to C. So I can find a holomorphic parametrization of it. Oh, yes, you're right. Okay. Okay, and then what happens to the same for you, yeah. Okay, and what happens to the dynamics? So now, so I was discussing Hénon maps. I say that it applies to F, so I will write F everywhere now, I hope. So F maps the stable manifold onto the stable manifold, fixing P. So when you look at F applied to psi PS of some point Z, so Z is in C, this is also a point of the stable manifold, and this F is one-to-one. So when you conjugate by this parametrization, it's a one-to-one holomorphic map from C to C, fixing the origin. It has to be like lambda times this. Okay, for some lambda. Okay. What? Oh, yes, sorry. Thank you, Laura. Okay. Okay, and what is this lambda? Lambda is an eigenvalue of the differential of F at P. And it's the one which is less than 1 if I take the stable manifold. Okay. Okay, and so what is the relationship between the stable manifold and the previous objects? You recover T plus from this stable manifolds, T minus maybe. Okay, so the point is that theorem is that what is it? It's stable manifolds of saddle periodic points are dense in J plus. So they are contained in J plus. They are dense in J plus. And integration on stable manifolds. So I will not define what it means. It's like what people call Nevanlina currents. Coincide with T plus. Okay, so the picture on the right here, let me try to enlarge this. So let me draw a picture like that. So the interior is K plus. Okay. Okay. So the boundary is J plus. And if you have a saddle periodic point P, then P is on the boundary. And you have the stable and unstable manifold. So the stable manifold here like that. Okay, so that's stable manifold of P. Okay, and it's contained, so it's a copy of C contained in J plus. Okay, but when I integrate over this stable manifold, I need to recover T plus. T plus, the support is J plus, so this stable manifold must be dense in J plus, and so the picture is like it comes back like that. Okay, and what I was drawing is like a foliation of J plus by these stable manifolds. Okay, it's not like that at all. So you should imagine like some kind of folds like that. And this type of folds, when you zoom, you see another fold like something like that. You know. And at each scale, you see this kind of folding properties. Okay. Okay, so I think I have enough material to state a first theorem. What we proved with Romain is so if F is as above, let's say F and G are automorphisms of C2 with positive entropy. And F is conjugate to G by some holomorphic diffeomorphism. So it's quite a strong assumption, okay? So it's for some holomorphic diffeomorphism of C2, then in fact phi is a polynomial automorphism of C2. Okay.
So here you're always assuming that we work with algebraic. Right?
So F and G are polynomial automorphisms. So F and G are algebraic maps. But phi is just holomorphic. So maybe phi involves the exponential function or something like that. But then the rigidity is automatically, you go from holomorphic to algebraic. And it's not, so what I say is that F is conjugate by G to G by something which is holomorphic, then F is conjugate to G by something which is polynomial. But in fact, it's a little bit stronger because you prove that phi itself is an automorphism. Okay, it's not another conjugacy which works, it's that one. Okay, then you can prove a better result. You can prove that in fact changing phi to phi composed with f or some power of f, in fact you can control the degree of phi by the degrees of f and g, okay, of the formulas. Okay, let's write a proof.
What's an example of a
so example to keep in mind, like x, y goes to x, y plus exponential of x. Okay, so this is a diffeomorphism because if I put a minus here, it's the inverse. Okay, and this is not algebraic because this one is not. Okay, so we need to rule out this type of example. Okay. Okay, so let's let us look at what can be proven in that case. So you see, so the dynamical features of F are transported to the one of G by phi. Okay, so phi of K plus of F will be K plus of G. Okay, so you have that. Maybe you should use that. Okay. So then you can pull back. I mean, you can maybe. I will do it in the wrong way for sure, but yeah, because yeah. So I think phi upper star of T plus of G is T minus of F times some positive constant. So, sorry, T plus of F. So why is it true? Because when I pull back T plus of G, I will get a closed positive current which is supported on K plus of F. Okay. I mean, the same is true for J plus, okay? So now I do it, I say it again. T plus of G is supported on J plus of G. So when I pull back, the pullback is a closed positive current which is supported on J plus of F. And by the rigidity theorem of Fornaes-Sibony, then it has to be this one. Okay. Okay, in fact, you can also show that phi maps saddle periodic points to saddle periodic points. And since the stable and unstable manifolds that determine T plus T minus, you can also use that to prove that you have such a relation by looking at the Neyron linear currents. Okay, so I used Fornaes-Sibony, but I could use the work of Bedford-Lubitsch-Smale. Okay, so then at the level of green functions, you get what? So G plus of G composed with phi, something like that, minus C times G plus of F is harmonic. Okay, it's pluriharmonic. Okay, I want to show that this is 0. Need to cheat. Okay, yes, of course. Okay, so if not, so you look at the function capital H, which is this difference. Okay, so it's pluriharmonic, so it's you can write it as the real part of some maybe holomorphic function. So H here is not a Hénon map, it's a holomorphic function on C2. Okay. Okay. And now this function H is 0 on, so I need to check J plus F. Okay. Okay, and I look at what happens along J plus of F. Okay. Okay, so the so you have, so this is contained in H equals 0, and this is foliated by the Riemann surfaces. H is as real part which is 0, which is so H is I times alpha for some alpha in R. Okay. So I have, let me say it again. I have a pluriharmonic map on C2. So it's a real analytic map, which is a real part of some holomorphic function. So it's a smooth map. Okay. This function, I assume it's not zero. So its zero set is a codimension 1 real analytic subset of C2. Okay, so you identify C2 to R4, and it's a codimension 1 real analytic subset. So there is no interior. Okay. So J plus is contained in this, and also K plus is contained in this. But in fact, K plus will coincide with J plus in that case because there is no interior. Okay. Okay, so it's contained in this. And this set is foliated by these Riemann surfaces. Okay, this is clear. I mean, if I look at the holomorphic function h being equal to this quantity for some alpha, which is real, then the real part along this Riemann surface is 0, and so h is 0, and that's it. And in fact, it's the only foliation by Riemann surfaces that this set supports. Okay, you cannot have another one because then somehow this set will be of dimension 4, not 3. Okay, so it is uniquely foliated by that. Okay, but we know a lot of Riemann surfaces in J plus F. We know all the stable manifolds. Okay. Okay, so let me say it again. J plus of F contains the stable manifolds, and H equals 0 contains these Riemann surfaces, but any Riemann surface which is contained in it is one of these. Okay, at least locally. Okay. Okay, so for any P among the saddle periodic points, the stable manifold of P is equal or contained in such a Riemann surface for some alpha. Okay. But this is a contradiction because this set is locally closed. You know, you are. I mean, if you take your point P here, you have the stable manifold. Okay, and it should locally coincide with a connected component of this. Okay, this set is closed, so maybe it's like that, and like that. But it's a closed analytic subset of my D square I'm zooming. And that one, WS of P, it has to be dense in J plus. So in fact, it comes back like this, and you get a contradiction. Okay. Okay. Okay, so now I know that, and this contradiction shows that I have this equality. Okay, so do the same. I'm using the fact that there is some kind of recurrence property of the stable manifold. I'm not even using the fact that it is dense. Okay. So for instance, if you know that the stable manifold intersects the unstable manifold somewhere, that you have a homoclinic intersection, then using the dynamics, you find infinitely many intersections near P, and this is already a contradiction. Okay. So do the same for G minus, and you get G minus composed with phi is equal to some other constant times G minus. Okay. And now you look at the function max of G plus and G minus. Okay, so here I'm cheating because there is a G and there is a... Okay, so this function at infinity, it behaves like log of xy. Okay. And the same for G max G plus F, G plus G, G minus G. Okay. Okay. But this function is almost invariant, you know, up to some multiplicative factor C, C prime. I can compare the function here and the function there, modulo composition by phi. Okay. And so what I get is that log of phi of xy is less than some constant log of xy. Okay. What does it mean? It means that the asymptotic behavior of this holomorphic map when xy is a large point, the norm is bounded from above by a power of the norm, like a polynomial map. Okay? And then by the Cauchy formula, you know that a holomorphic function which behaves asymptotically like a polynomial map is a polynomial. Okay, you just have to write Cauchy formula to conclude that phi is polynomial map. Or you just put a square. Okay, so I wanted to give this proof. The details of this proof, because you see in this example arguments that are coming back and coming back again and again. So you have some complex analysis and some rigidity of coming from the pluripotential theory. You see that I was using these ideas of foliations by Riemann surfaces, okay? And otherwise basic arguments coming from, I mean, basic if you know Pessin theory, okay? Okay, stable manifolds and things like that. Okay, so now let me state a more interesting theorem. So this one is easy, but before I do that, I need two definitions. Okay, so what is a slice of J plus by a holomorphic disk? Gamma. So what I mean by a slice, I should say a non-trivial slice. Okay, so I draw my picture again. So this is J plus. And now I take a holomorphic disk. So it's the image of the unit disk by some holomorphic map with values into C2. So here is my disk. Okay. Okay. And I have a non-trivial slice if the intersection of that I see between J plus and gamma is like that. So I want gamma intersected with G plus to be non-empty. Okay, and more precisely, I want gamma not to be contained in J plus. Okay, so there are some issues here that I am hiding. Technicalities. Okay, but assume for simplicity, which is something we will prove never happens, but assume that this is a smooth, let's say, C1 curve. Then the picture is like that. So you have gamma, you have J plus intersected with gamma, which is a smooth curve. Okay, and then you have so we are on the boundary of K plus. So maybe locally in gamma, J plus coincide with K plus. Okay, or what? So and then G plus is positive on both sides, or Okay, or on one side, G plus has to be positive because it has to be positive somewhere. We are on the boundary, and on the other side, it has to be 0. And so here we are in K plus. Okay, so that's the picture you should have in mind in the case where it is smooth. Okay, but the theorem tells, so let F be a polynomial automorphism with positive entropy. Okay. First result is so I'm okay. Is never a smooth curve or even rectifiable curve. Okay. Okay, so this is something which is true for polynomial automorphisms of C2, but which is not true for polynomial transformations of C. Okay, because Z goes to Z to the D. The Julia set is a unit circle, and what you see is a smooth curve. Okay. If there is, there is no global real analytic foliation f of C2 such that for any p saddle periodic points, the stable manifold of P is a leaf of F. And 3, okay, what is 3? Assume
that all of the leaves are not, or just that if you take one,
it's the same.
You can't extend it.
It's the same.
So it's true about
yeah, you can just take one, but I wrote for all. What I have in mind is
one of them, you can't extend it.
so there is no global real analytic foliation F such that J plus is stable under F. That is, if you have a point in J plus, and the leaf of F through that point is contained in J plus. Okay, so that's somehow the strongest assumption concerning F. Then you have another one which is for every saddle periodic point, WS is a leaf of F, or is locally contained in a leaf of F. So that's somehow a weaker way to state it. Or another one is for one saddle periodic point. Well, all of them are equivalent. Okay. So assume that. So here, unfortunately, we don't have a general result, but assume that F has a saddle periodic point P with as unstable eigenvalue which is not in R, and the stable eigenvalue which is not in R either. Okay, so the two eigenvalues you see for the differential of the nth iterate, where n is a period of F at P, these two eigenvalues are complex numbers but not real. Okay, so there is some kind of angle. Okay. Then, if F is conjugate to G for some real analytic diffeomorphism, automatically F is conjugate to G or G bar, the complex conjugate of G in the group of automorphisms. Okay. So here, what is the issue here? It's if you take phi to be xy goes to x bar y bar, you conjugate f to its complex conjugate. Okay, so you can never conclude that f is conjugate to g. It has to be conjugate to g or g bar. Okay. Okay, so that's the kind of conclusion you want to achieve, and in fact you do so. So if you have a real analytic conjugacy, then in fact you have an algebraic conjugacy. Okay, so it's not a really deep statement because I mean this assumption is quite strong. Okay, but the mixture of ideas is nice, I think. So I wanted to explain a little bit how the ideas go. Why did I state the three statements in one theorem? It's because, in fact, 1 implies 2 and 1 plus 2 implies 3. Okay? Modulo what we know for Hénon maps. Okay. G bar, you put bar on the coefficients, yes. Or you conjugate by xy goes to x bar, y bar. It's the same. Yeah. Okay. Okay, so one thing I need to say is if you look at C1 conjugacy, so the paper we wrote afterwards tells you that you can look at, you fix F, you assume that it has positive entropy, that's it. No assumption on the periodic points, okay? And you look at the set of automorphisms G, which are conjugate to F by a C1 map, modulo holomorphic conjugacy. Okay. Of course, you can always do algebraic conjugacies. Okay. So you have to look at it modulo algebraic conjugacies. Then this set is finite. You start with F. Maybe there is finitely many, I don't know how many maps which are not related to F but are C1 conjugate to F and are not algebraically conjugate to F. This can happen, but this set is finite. Okay. So this is something that maybe Romain will explain, and which is consequence of another technique, and which is using this multiplier rigidity that he will talk about. Okay. Okay. And I think that's it. So I will stop. But yes, 1 implies 2 with the work of Brunella. 1 plus 2 implies 3 with all the work of Bedford, Lubitsch, Smiley. Plus what we did. I mean, okay.
Questions?
So I was just curious if you've done anything on like rigidity in the parameter space. So what I thought of was like usually Mo has this inhomogeneity of the Mandelbrot set resolved. No piece of the boundary of the Mandelbrot set is holomorphically identifiable with a different piece of the boundary of the Mandelbrot set.
No, we don't have that. I think we don't have something like that. I mean, I never looked at it, so I cannot say. Maybe you can ask your question to Romain next week, but I think we don't have anything like that yet. Okay. There is one thing I want to add. Maybe it's a result by Bedford and Kim that we used. And I would be happy if someone had a simple proof of that. So you start to so the theorem is like this. Let F be so let F out C2. So I will give a statement which is not exactly what they prove, and then I will correct the statement. Okay. So with positive entropy. Okay. It is not possible that the unstable multipliers of all fixed points be equal. Okay. you look at all fixed points, assume that, and you compute the unstable multipliers. Okay, these eigenvalues lambda u at the fixed point. Okay, and assume that there is some complex number alpha such that lambda u p is equal to alpha for every fixed point p. Then this property is not possible. Okay, in fact, you need f to be conjugate to a composition of at least 3 Hénon maps. But I'm not sure that it is necessary. Okay, it's some kind of technical issue. And the conclusion is better than what I wrote, that of all fixed points except maybe one are equal. Okay. So you list the fixed points, compute the eigenvalues. If you see always the same one, except maybe for one fixed point, then this phenomenon is not possible. Okay, and it's completely algebraic statement, and they use Grobner basis, a lot of computation, and understand nothing. Okay. And if you have a reason why this should be true, I'm quite interesting. So this is Bedford-Kim. It's amazing. Okay, it's something which is not correct for polynomial in one variable. You know, if you take z goes to z to the d, the fixed points are what? So you have the origin and you have roots of unity. And then the multiplier at the roots of unity, you see d. And you see 0 at the origin. So you are in this context. Okay. So if you have this property for a map which is a one variable polynomial, then you can look, the map is conjugate to f of z is like a beta z plus z to the d, up to conjugacy. Okay, so there are examples like that. In dimension 1, in dimension 2, this is not possible. And this is, at the end, this is the reason why there are no invariant holomorphic.
You really need this composition of 3 maps?
Yes, but this type of properties, you see, they are stable by iterations.
But do we know if
No, if f is just one Hénon map, I don't know. But, yeah. I don't remember exactly what is known. Maybe if the degree is large enough, I don't remember.
Maybe here the right analogy would be to compare it with the rational maps on the right. Automorphisms are,
Rational map.
Sorry, endomorphisms of projective space.
To compare this with endomorphisms of projective space? No, no way.
No.
Never do that.
No, this resulting from dimension 1. I mean, these are not automorphisms, so somehow I think once you get to
Oh yes.
more,
Yeah, but it's a polynomial map.
that's true.
No, I mean, automorphisms of C2, they do not behave as rational maps in dimension 1. Yeah, it's closer to polynomial maps in dimension 1. Now, the Julia set is a compact set. You have attracting fixed point at infinity. You have globally defined Green functions. So there are many phenomena that you see for rational maps that you don't see for automorphisms or polynomial maps.
Oh, sorry. If you remove the condition on both eigenvalues being non-real, does this scale to hold?
I don't know. I mean, I think if you remove this property here, the same statement is correct, but I don't have a proof. That's it. There is some kind of technical issue at some point, and I don't know how to do it.
So you don't have a classification of Hénon maps with real eigenvalues?
Oh no, I don't have that. That's okay. That's also something I should say. Yes, this is also related to this, but I think maybe Romain will talk about that. I didn't want to talk about multipliers in this talk, but for instance, here you start with the assumption is one saddle periodic point P with this property that the multipliers are not real, and from that and dynamics, let's say horseshoe dynamics, you construct a set of points which is infinite of an infinite set of saddle periodic points with the same property. You start with one, you end up with infinitely many of them. And better than that, you can show that this infinite set is dense in C2 for the real analytic topology. So these infinitely many points are not contained in a real analytic hypersurface because of this type of argument. Okay.
Does it have a periodic point immediately implies positive entropy, or you need to?
Yes, because you have an automorphism of C2. You know, an automorphism of C2 with entropy equal to 0, the dynamics is quite poor. Okay, but abstractly, I don't think so. For instance, I mean, I don't know if we know the answer. So you start with, let's say, you start with a holomorphic diffeomorphism of C2 with this type of property. So infinitely many saddle periodic points with this. Does it have positive entropy? I don't know.
Yeah.
I have a question about the very beginning of your talk. You pointed out this: if two maps, share an parameter orbit, then they're basically the same map. What if you just have a Zariski dense intersection between an orbit of?
Okay, so then I don't remember exactly who did that. Gyoka, Tucker also, and I think there are three of them, no? Ziv, yes, Gyoka, Tucker, Ziv. They have two papers. Yes, but many arguments can be copied for Hénon maps. I think nobody did that, but for instance, the argument I gave when you have equality of the sets, it works for Hénon maps because the theory of heights goes well. Okay, for K3 surface automorphisms, it goes well. If you just ask that the intersection be Zariski dense, then you have to be more careful, and there are two nice papers by Gyoka, Tucker, and Ziv on this subject for P1. Yeah.
Maybe that's polynomials, don't they? So
Yeah, maybe. I think they use red theory, so.
Yes, you're right. You're right. Polynomial maps. Yeah. Yes. You're right. Right. Yes. Thank you. Yeah.